And good afternoon, everyone. Thanks for joining another ATS University session. If this is your first time, my name is Zach with ATS. I'm our National Sales Manager or National Accounts Manager for the Market Development team. I work with our Spec Tool software program and work with engineers and architects and design build contractors across the US, as well as across Canada, in helping them get set up on our Spec Tool. One of my other privileges of the role is working with our ATS University session. We run a almost weekly, basically 2 or 3 times a month. We put together a topic of interest and host a webinar for those that are able to join us. And with me today is Colin Marshall, Systems Engineering Manager at Watts, who's going to be going over our topic of snow melting and ice prevention. Thanks for joining us, Colin.
I'm glad to be here.
Yeah, should be a good one.
Yeah.
This is going to be an ASPE accredited CEU, as you can see at the top. So we're going to be fairly non-branded through the presentation. At the end of the session, I'll show you how you can find the products and any of the products that we talk about during our sessions. I'll show you how you can find them on the ATS Spec Tool at the end of the session. If you're unfamiliar with the ATS Spec Tool, thanks for joining the session with, I guess, a little information. But hopefully you stick around, learn something, and then we can show you how the Spec Tool can save you time and save you some frustration along the way. It's a free product selector tool that allows you to configure your actual product selections and then download the output format that best fits your go-to-market method. So it could be written specs, could be configured cut sheets, could be fixture schedules or Revit files. All of that's free and available on the ATS Spec Tool platform. A couple of bits of housekeeping before we dive into the session today. We do have everyone muted upon entry, pretty standard protocol these days. We'll of course be keeping track of those that joined the session, and my team will be sending out a certificate of attendance so that you can self-report for your ASPE CEU hours. This is an accredited CEU, so if you need those, you can use it for that. If you are just doing the non-accredited CPD hour style, which is very regional, depending on whether or not you need the accreditation, then of course you can just use our typical certificate of attendance that I'm sure you've received before. If you have any questions after the session, please feel free to reach out to me, zach@atspec.com, and I'll be keeping an eye on the questions along the way, and I'll raise them up to Colin when we get into the appropriate time. But yeah, I'll pass it over to you, Colin. Let's see what we got.
Awesome. Appreciate that. I want to thank everybody for taking the time to join us today. And if you do have questions, I do encourage you to type them out into the chat, and we'll get to them as we go through. I want to encourage you to ask questions, because if you have questions and you leave today and you still have questions, then this session didn't really do you a lot of good. So hopefully you have a lot of questions, and trust me, I enjoy running down those rabbit holes. Snow melting is an application that's near and dear to my heart. I've been doing it for almost 30 years, and it really is one of those cool, fun applications that has a lot of real world benefits for a lot of different reasons. And hopefully today we'll dive into that, talk a little bit about the why behind the how, figure out why we're doing things, how it works. And a lot of times with snow melting systems, there are no two systems that are going to be exactly the same. You're going to design systems based on customer need, application requirements. You're going to design them for responsivity, frequency of use. There's a lot of factors that go into snow melt systems. So what one person does may or may not be applicable to the system next door. And hopefully we'll kind of touch on why that is and how it can vary from project to project. Colin Marshall, as we said, I've been with Watts, been in the industry really since 1995, been around, seen a few things, done a few things. This is kind of the highlight of where the chat is in your presentation screen. And let's dive into it. So starting off with a poll question right off the bat, how many snowmelt projects have you been involved in? So basically what we're looking for here is what the experience level is of those attending. We'll give it
we'll give it a minute to
10
see,
seconds.
What people come in with. Nothing coming so far. Maybe it's a fresh
Okay,
audience to snow melt.
that's okay. If this is new, this is the perfect intro experience for that. Where are we using snowmelt systems? Well, there are a lot of reasons and locations to use a snowmelt system. Commercially speaking, is probably one of the largest areas that we see snowmelt, and you're going to see them in emergency locations for hospitals, maybe accessibility access locations, helicopter pads. The helicopter pads are kind of interesting. A lot of times, for a hospital, they have the helicopter pads on the roof. Those are done for the safety of the occupants, the trauma units that are coming out to the helicopter to receive a patient. You want to make sure the area is clear, obviously, so you avoid slipping and hazards there. But it's also done for the safety of the helicopter. The jet wash, the downward wash from the helicopter as it's landing or taking off is going to kick up snow and debris. That debris has the potential to damage the helicopter itself if it gets lodged into a rotor somewhere. It also is a risk for those on the outside of the building, on the sidewalk down below. Debris is kicked up and it kicks over the edge and it falls. If you look at any helicopter pad that is on top of a building, there's typically netting that goes around the building. That is to help prevent that debris from falling over the edge. Snowmelt systems greatly reduce the amount of debris that is present to be kicked around. So some other reasons to look at a snowmelt system. Car washes. We see this a lot on the exit ramps of car washes, and it doesn't have to be snowing to utilize a snowmelt system. On car washes, it could be 20 degrees outside and cars are coming out of the car wash dripping with water. It hits a cold pavement and it will freeze. And pretty soon, after a couple of cars, you end up with black ice on the exit apron. Next car comes out, hits the black ice, and has the potential to slide into oncoming traffic. So there's a safety factor that comes with snow removal and ice removal systems as well. A lot of different reasons that are going to motivate us. On residential applications, you'll see the same needs, but it's more for a micro purpose. You're trying to eliminate snow from the driveway for convenience. Sometimes in certain areas of the US, there are requirements that if the incline of the driveway is greater than 7% of a grade, you have to snow melt, because that introduces a safety hazard again for the occupants using the driveway and for those at the bottom. Sometimes you're looking at environmental reasons. In certain areas of the US, you have environmental reasons says you cannot use artificial melting means, i.e. salt and or other chemicals, to remove ice and snow if you are within so many yards of a waterway, a creek bed, a river, something along those lines, because those chemicals have the potential to wash off of the snowmelt area and into the waterway. So you got to be aware of that as well.
I was gonna say, similar to that parking garage, the parking area question you mentioned for
Mhm.
the US. I know in Canada, we have a higher predominance of underground parking. And similarly to the ramps that are going up for certain parkings in the US, you'll find snow melt on the ramp going down into
Correct.
the underground parking, correct?
Correct. You'll find them coming into and out of the parking garage for various reasons, either to prevent sliding into traffic or sliding down into the storage unit or the parking garage.
Yeah. And then
Um,
we did have a couple of people coming back with some of their snow melt experience, and it was actually one of your first applications that you mentioned with the airport or the rooftop design. We had
mhm.
a couple of people commenting about their experience in putting together roofing plans and how that tied in. But I was shocked by your note about the netting. I had no idea it was for the helicopter pads. I thought it was a very different reason. I thought it was like a safety thing that the airport required. Don't fall off the roof. That was
And
always
I'm
one.
sure that's part of it. I mean, I'm sure there's multiple reasons to have
Yeah,
it, but that is one of them, is for the debris for the occupants down at the bottom of the building.
that makes a
Yeah.
lot of sense.
And it makes you wonder that that has come about because that has happened. right? All the safety to things that we deal with today is because something's happened that's invoked the safety measure, right?
Yeah, interesting.
The other thing that comes into play with snowmelt systems is safety of the occupants, not because you're in a vehicle, but because you are actually having to physically remove the snow some way or another. On residential applications, you're out there potentially physically shoveling snow. There was a statistic that says how many people who actually end up with health issues every winter from simply shoveling snow. As occupants and get older, their ability to do physical labor like that, especially physical labor that is um, unusual and out of the norm as a snowfall event would be, that's a risk. Um, it's also a risk for the driveway itself. So let's say we have a snowplow. Maybe it is a blade on the front of our tractor or whatever the case may be that is going to blade the snow. And you have a sand and brick paver driveway. Well, you have to leave that blade up high enough to not catch the brick pavers. Otherwise, you're digging up your driveway as you snowplow. So if you have to leave the blade up high enough where you're still leaving snow and ice behind, and it actually ends up becoming worse because now it's compacted, right, and becomes slicker as it thaw freeze cycle over the next couple of days. So these all become factors. A snowmelt system allows you to have a snow and ice free surface without the risk to the actual paver system. You have decorative concretes, you have sanded brick pavers again, and you're using salts on those items. The salts will start to corrode and etch away the finishes over time. Same thing happens with inside of lobbies, let's say for hotels. You throw snow or throw salt on the snow melt outside, and occupants are walking in, they're picking up the salt in their shoes and they track it into the building. And now on top of your terrazzo tile, you have salt that starts to etch away your flooring. So the benefits are not just external, they can also be internal. It could be for carpet as well. It doesn't have to be tile. You get salt ground in the carpet as well. So a lot of secondary benefits to snow melting systems. So safety, we talked about safety. Safety is from shoveling, the actual act of removing the snow. Obviously, the most obvious safety hazard is you eliminate the ice, you eliminate the risk for slips and falls. A lot of times, we think about horizontal or plane activities or locations like what we see in the sidewalk here, but really slips and falls happen more on stairs. And it's real hard to shovel and blade stairs. So a lot of times the stairs are the areas that get the least amount of attention, and they're the ones that have the highest risk of falls. Snowmelt systems are able to be installed. You can typically conform the piping to meet the profile of the stairs. And so you get a nice even melting across the tread and the riser of the steps. Retail spaces are going to look at optimizing their point of use. Outdoor dining, especially in like ski lodge areas, are big. People like to sit outside and view an area. You want to make sure that area is as clean, as clear as possible. Also, on commercial applications, one of the things that you have to contend with is the labor to remove the snow and the time at which the snowfall happens. If you are a business that requires your entryways or your point of use to be clear of snow at 8 a.m. and it starts snowing at 4 a.m., well, nobody is physically there to remove the snow unless somebody either A, lives on site or is on duty to come in and take care of that. And that is not a convenience. So snowmelt systems are automatic. They will be able to be turned on remotely or automatically through sensors to start melting snow. And like I said before, access ramps are a big area for snowmelt systems. You want areas that are safety focused to be as clear and removed of the hazards as much as possible. I already kind of talked about this one. I jumped the gun a little bit. Anything that's textured, architectural speaking, you don't want to put chemicals on those surfaces, and you don't want to risk it mechanically by ripping up and damaging a surface. Okay, what industries are requesting snowmelt solutions? In your area, what do you hear the requests to be? Are you seeing them on residential? Are you seeing them more in a commercial application? What car washes, helipads, hospitals? What is it that's driving your interest in snowmelt?
We had a couple of people coming in with some of their applications. We had a great story from one of the persons saying that they had a park monument with a Huey H1N1 installed 45 feet in the air, needed ice melt precautions and prevention system in case they needed it. And then they needed it when they got like 18 inches of snow and minus 20 temps. It's the outlier situation, but it comes up, right? And then
Hmm.
a lot of people talk about like sloped roofs and how they need ice damming or to prevent partially melted snow falling, handy ramps in handy or ADA areas.
Hmm.
Uh, and there's a couple of installation questions that we'll get to when we come up to like some of the products, particularly around manifolds.
Hmm.
So we'll bring those up when that comes up. But then a lot of people just saying like the commercial roof design and ice melt. And I know some of the people that, or some of the projects I've worked on with engineers, either on the call or from their firms in the past, a lot of healthcare and ambulatory areas
Yep.
requiring the emergency ramps to all be treated.
Yeah. Roof load, you mentioned roofs. Obviously, one of the big issues with roofs on metal roofs is snowfall sliding off, right? So it dams up, dam breaks, and now you have this torrential amount of snow falling all at once. If you can keep that melted or at least controlled, that is a big safety plus. The other thing with roofs, which can happen in certain areas, is weight. You need to stay on top of the snow on the roof to keep the weight load down. If the snowfall gets too heavy, then a lot of times you have to get up there and physically remove it off of the roof. And that is just another hazard that you as an individual have to trespass and just make sure that you don't fall. Okay, so financially, in some areas, snowmelt systems are considered safety enhancements. And if you are increasing the safety of a location and you're reducing the risk, you can sometimes get financial breaks from insurance companies. They will see those as a liability reduction and can actually give you a break on insurance, depending upon the location and the insurance company. It's a lot like fire sprinkler systems have become over the years. If you install a fire sprinkler system, you've reduced the risk and the hazard of a fire doing multiple or extensive damage to a structure. The other thing that happens financially is if you do have an event, if you do have somebody who falls, if you do have an employee who has an incident on site, there are long-term ramifications that can come back to that event. They fall, they injure themselves, there's medical issues that come up, there's potential lawsuits from individuals who fall at a commercial location. These are all things that have real financial dollars associated with them. Okay, considerations for snowmelt. There are two main types of snowmelt systems that you can use. There is hydronic applications and systems, and there are electric systems. Both are valid and both have pros and cons. Um, Hydronic systems are typically what we think of when we think about snowmelt systems. And the reason why is that they're typically larger areas. we talk about snowmelt systems as being parking garages, as parking areas, as ramps. They're typically larger locations. Hydronic systems have more parts and pieces. There's tubing that goes in the construction, the concrete, the sand and brick pavers. There are supply and return lines to manifolds. There's a boiler, typically. There's mechanical piping. There's glycol that gets added to the system to prevent freezing. A lot of components involved with that. There's also a lot more maintenance involved with a hydronic system. You're dealing with glycol. So glycol systems typically require more annual testing, and they potentially will require the system be flushed and refilled more frequently because the glycol will age over time. Electric systems typically just have the cable that goes in the slab or in the snowmelt area. There's no supply and return piping. There is no mechanical room. You're tying it into the electrical supply, and you still have a sensor and you have the controls that automatically turn it on and off, but it's almost isolated to the snowmelt area itself. So it simplifies the installation, and it also simplifies the long-term maintenance. There is nothing to maintain in an electric system. There's no fluid, no glycol, no anything else that has to be considered. No pumps, no boilers. So it's really kind of a self-contained solution. Both will provide roughly the same amount of melting capacity. Hydronic systems, however, have the ability to be adjustable. You can adjust the fluid temperature. You can adjust the tube spacing. You can adjust a few things from a design standpoint to overcome certain elemental conditions, whether it's snowfall amount or the construction profile itself, as the tubing is installed in a slab, for example. The deeper the tubing is, the higher the water temperature needs to be. On an electric system, it's typically a fixed wire temp. It's going to be 140 degrees or 130 degrees, or whatever the design is for that particular product. And it's fixed. There is no adjusting of that temperature. So depth variances are going to potentially be factors to the final surface temp of the snowmelt. Now, the good thing is that these systems are typically over-designed and over-capacitated so that those variances that we know happen in installation are not factors from a performance standpoint.
So just a question
Yep.
there when it comes to electric versus hydronic. You mentioned the larger areas that hydronics are typically used for. Is there a maximum area for an electric system?
No. Really, at that point, your electric is the size of the electric system is going to be driven by the power available on site. You have so many watts per square foot, 35 to 50 watts per square foot to melt snow per square foot. And that equates into so many amps at a voltage. And as long as we have the power supply, we can do as large of an area as we want. I have done parking lots, 10,000 square feet of parking area at a location because it was a casino. And to them, in order to install a hydronic system, it meant disrupting the casino. Basically, the mechanical room was in the middle of the building. They would have to figure out how to get supply and return lines out to the snowmelt area. They would have to dig up the grounds in order to do that. There was a lot of issues with the physicality of installation. An electric system was pretty much isolated to just the parking lot. They had power located everywhere on site, and they just had to tap into it. And they had plenty of power capacity, so they could do the full area. But generally speaking, that is what's going to limit the size. Normally, you can go as big as you want with a hydronic system because we just up the boiler size, right? We have a little bit more design flexibility on that. Conversely, though, electric systems have a greater advantage on small areas. Boilers, mechanical room setups, the added fluid with the glycol, The biggest cost of a hydronic system is the mechanical room. The boiler, the pumps, the expansion tanks, all those things are the bulk of the cost. And if you do a small area, say 1,000 square feet for a driveway, the majority of the cost is in the mechanical room. And there really isn't a large cost jump in boiler sizes at that size. So if you go from a 50,000 BTU boiler to a 75,000 BTU boiler, there isn't a huge price difference in that mechanical room. It's taken the lion's share. Electrical systems really excel in cost savings on small areas. Usually the trade-off is around 1,500 to 3,000 square feet. That's going to be the gray area between whether or not it's more advantageous for one or the other. Under 3,000 square feet, it's going to be electric. Above that, it's going to be hydronic typically. 1,500 to 3,000 is kind of gray. They kind of overlap as cost goes and system needs are. But that's kind of the breakout that I've seen. Installation wise, you're installing both products basically the same. They both go in the actual medium of the driveway or the snowmelt area. If it's in a concrete slab, it's being embedded in the concrete. If it's sand and brick pavers, it's going in the sand layer. It's just, they're real similar in that from an installation standpoint. The cables are smaller. They're going to be spaced closer together than hydronic tubing is. But that's really about the big difference there. Well, we kind of touched on this a little bit. Typically, electric systems, they're going to be lower installation costs because of the mechanical aspects of it, because you have fewer moving parts, so to speak, and really ideal for the smaller areas. Disadvantage can be, but not is always the case, operating cost. Electric systems, because we are using electricity, the cost per kilowatt generally is going to be higher than a cost per, let's say, a therm of gas. Hydronic systems have a broader flexibility on what we use as a natural resource. You can use an electric boiler, you can use a natural gas boiler, you can use a waste oil boiler, you can use a wood-fired boiler. A lot of variables go in and options go into that boiler selection, which drive operational costs. And you can become more or less cost effective depending upon those options that you choose. Electric systems, we're pretty much locked into what the going rate is for electricity in our area. Some areas do have really good and inexpensive electric costs, so that could be a deciding factor. Conversely, almost everything on a hydronic system is going to be opposite of an electric system. Advantages, typically lower operating costs, fuel choices, I mentioned, design flexibility, but it can have higher installation costs because there's more parts and pieces, and depending on the square footage, your cost per square foot is going to vary greatly. Electric systems are usually pretty flat on the cost per square foot, whether it's 1,000 square feet or 10,000 square feet, your cost per square foot is almost exactly the same. Okay, the mechanics behind what we're doing, how a snowmelt system actually works. There are four main components to a snowmelt system. You have actually the melting, which is what is referred to as the heat of fusion. We're converting a solid, i.e. snow and or ice, into a liquid, water. Once it reaches the water state, then we're dealing with evaporative losses. So we're adding energy to the water and it's going to evaporate into the atmosphere. You have heat losses that are associated with a dry surface and you're just venting black body losses into the sky, or back and edge losses, which are going down into the ground beneath the snowmelt and off to the sides. Snowmelt systems are unique in the sense that we are not trying to retain any energy. One thing that I've learned, or that I see a lot of times, is people try to equate a snowmelt system with a hydronic heating system. They both use hydronic. They are both water-based, let's say, both use boilers, real similar in design and sense of the components that are used, but the application is greatly different. In a heating system, I'm trying to retain the heat in an enclosed space, i.e. my building. And so the mechanics of energy transfer from the floor into the space and then from the space out into Mother Nature is different than the snowmelt system. Snowmelt system is always venting the Mother Earth and out into space. Heating systems also, I am retaining that because I'm heating all the time. Anytime it drops below 65 degrees outside, I'm trying to maintain a heated environment, and that will last all winter long. Snowmelt systems operate half a dozen times a year. It only runs when it snows. I'm not trying to maintain an environment. And with the advent of better controls these days, I get better performance because of the controls as well. So, but it could be weeks, if not months, between cycles on operation because it's only going to run when it snows. And then, of course, as mentioned, the environment. When is it snowing? How much does it snow? Is it snowing 6 inches or is it snowing 18 inches? And that is a variable that is impossible to design around. I have a saying I like to use, and that is engineering is the art of the best guess. It is. It's a swag. We're taking a variable component and we're trying to apply an instantaneous moment in time to a design. I'm throwing in my calculations that it's 30 degrees outside and it's going to snow 12 inches. How many BTUs do I need to supply? Well, how often is it 30 degrees outside and snowing? How often does it snow 12 inches? I don't know. ASHRAE shows us what the historical data is. And in my area, my historical data is average temperature is -3 degrees with an average snowfall of 8 inches. Great. I guarantee you it's not -3 degrees every day of the winter. And it doesn't snow 8 inches every time it snows. Sometimes it snows 4 inches and sometimes it's 18. Those variables impact my snowmelt design. Bummer is it's already installed. What changes from a performance standpoint from when I designed it to what it actually is doing in the field under reality? And the good thing there is the thing that changes is time. So the amount of energy to melt snow is basically the same. It's going to have X amount of BTUs to convert this snowfall into water. If I go from 6 to 12 inches, my loads from a calculation standpoint go up. Part of that is because I'm trying to compress that 18 inches of snowfall into the same amount of time from a consistency standpoint. So I'm looking at a 2-hour window of melting. So 6 inches and 12 inches or 18 inches all need to melt over 2 hours from a design calculation standpoint. The reality is in the field, my time is going to go from an hour and a half to 3 hours. It's a swag. It will melt. It's just the heavier snowfalls take a little bit longer. Do we notice that? Typically not. It's never a situation where it's critical that we hit that target. My main goal is that it removes the snow. That's the goal. If criticality is an issue and we need to have responsivity, now our controls come into play. We're looking at controls that have an anticipatory feature to them. The controls we use today, most of them have some sort of Wi-Fi integration that allows it to tie into the internet and connect to weather apps. And those weather services tell the controller, hey, a snow system is coming. These are the conditions. This is when it's supposed to start snowing. And the smart controller now says, well, the app says it's going to start snowing at 6 p.m. I'm going to turn on at 4 p.m. so that my system is ready to receive snow and melt snow at 6. it anticipates, and so it's more responsive. And anymore, even with all those variabilities, snowmelt systems are really, really responsive. Anyhow, these are factors that drive the variability in design, and where we end up on how many BTUs we need to design for. Part of our guessing process is we look at a couple of factors. One of them is the free area ratio. And that basically says, how much of the snowfall am I going to try and keep up with? We break these into three classes, class 1, 2, and 3. And basically class 1 says, it's a non-critical area. I'm going to allow all of the snow that I'm designing for, say 12 inches, to accumulate. And then the snowmelt system will pick up and melt over time. This is the slowest responding system that we have. It comes up to temperature fairly slow. It's using the lowest amount of BTUs, and it's going to take the longest to actually clear the driveway. Then you have a class 2 or a 0.5, and it says I'm going to keep up with half of the snowfall as it falls, and then the other half after snowfall stops. And then a class 3 or a 1 ratio is no snow buildup at all. It is the most free area of snow possible. There's no buildup. These are things that we're going to use for the emergency ramps, the hospital access areas, maybe geriatrics facilities where it's critical that there's no risk of slippage. That'll be a class 3. They will typically have the highest BTU loads and the quickest response of a system from start to finish. And then we have a factor that dives into my percentage of accuracy. So I'm designing for 12 inches of snowfall. How confident am I that I'm going to always get 12 inches of snowfall? And we typically design anywhere between 90% and 100%. Obviously, at 100%, I'm saying I'm 100% certain that I'm always going to have at least 12 inches of snowfall. And it will typically drive my snowmelt load up because it's pretty accurate on what it's trying to melt for. If I say, I'm 95% accurate on my 12 inches, that means there is some variable that says I'm going to get a 6-inch snowfall and a little bit that's going to get an 18-inch snowfall. But overall, I'm going to have about a 12-inch average. But there's a variability on individual snowfall events. That will factor in a smaller or a lower overall BTU load because I'm accepting the fact that on the lower snowfall side, the system's going to respond faster. And on the higher snowfall side, the system's going to respond a little bit slower. It's factors that allow me to try and optimize my design. Insulation. Insulation is one of those topics that comes up all the time on a snowmelt system. And if you ask 10 designers, you're going to get 10 different answers. Whether or not, do I insulate or don't I insulate? Do I do this or don't I do this? And the answer is always going to be, it depends. Part of it is what do I want? How do I want the system to respond, to perform? Part of it also is trying to understand what can happen to the system and what does it mean to insulate and not, from not only system design, maybe cost of operation, cost of installation. All these things play a factor. It's not just about responsivity. So let's take an example here. I have a bridge. Bridges are notorious for icing over first. They ice over first because they have a higher heat loss. They are decoupled from Mother Earth. They are elevated in the air. They have multiple exposures to wind loss and atmospheric losses. They have no thermal mass associated with them. The aprons on either side of the bridge in this picture, they are in contact with the ground. The ground is a thermal storage device. Roadways that are in contact with the ground are going to freeze later than the bridge will. Snowmelt systems operate the same way. If I don't insulate a snowmelt system, it's going to impact the response because I have a sensible and a latent load. I first have to raise the slab temperature up to melting. If the slab temperature is 20 degrees, I have to get it up to 32 degrees before it can melt. I'm dumping energy into that mass, the concrete, to bring the mass temperature up. If the concrete is sitting directly on the ground becomes part of my mass. The ground is also at 30 degrees or 20 degrees or whatever the case is. Some energy will go down into the ground below. Once that ground temperature comes up, heat transfer is from a high temp to a low temp. The delta between point A and point B is what drives heat transfer. Once the ground comes up to temperature, there's no delta. There's no more heat loss down. All the heat loss is going to be up into the surface of the slab. So there's a response factor there. Totally noted. So we overcome that maybe with an early start, or you can overcome that by just letting it run longer. The longer it runs, the more BTUs it pulls. Absolutely true. Insulate that slab, and you decouple the slab from the earth below. It will respond faster. Here's the caveat. The quicker a snowmelt system comes up to temperature, the quicker it's going to cool when the system shuts off. So all of that energy I dumped into the ground beneath my slab without insulation, when it comes up to temp finally and is melting, it's kind of like the difference between a Mack truck and a Pinto. Which one stops first? Well, it's going to be the Pinto. The Mack truck's not going to stop very fast. A snowmelt system without insulation is going to coast. Once that snow is clear of the surface, the system shuts off. But just because we shut the system off doesn't mean it instantly cools. It's going to give off that energy slowly over time, and it slowly will cool. And it takes longer for it to drop back down in temperature. Why is that important? It's important because of residual water. When we melt snow, we create water, and that water flows somewhere. It's going to maybe flow off the side. It's going to flow downhill. We got to have a way to remove the water from the snowmelt area. If we shut off the snowmelt system and it cools too quickly, that residual water has the potential to turn into black ice. And we actually end up creating a hazard that we were actually trying to avoid. So if we insulate it, we have a quicker response, but we have to adjust our controllers to run longer after the snowfall event has stopped in order to prevent the black ice from forming. So that's one variance. The other variance is just frost. When you decouple the snowmelt area from the earth, those fall days, those shoulder days where you actually end up with frost and ice buildup, like on your car windshield, will actually form on your snowmelt area. It's not a precipitation event. It's not going to trigger the sensor into turning the system on, but you can actually have ice buildup because of frosting on the surface because it's decoupled and doesn't have that residual thermal mass effect. So some things to take into consideration there. The other thing that we want to look at is vehicular loading. Let me see here. Nope, I'm getting ahead of myself. Vehicular loading. When you look at insulation, insulation is going to compress. If you have an area that has foot traffic, that's a certain amount of weight on that slab. If you have an area that has car traffic, that's a different amount of weight. If you have an area that has semi-traffic, that's a different kind of weight. 1 inch insulation board, extruded polystyrene, has a compressive strength of 25 psi. 2 inches of extruded polystyrene has a compressive strength of 100 psi. You have to choose the insulation for the loading factor, static and dynamic, on the snowmelt area. And the reason why you need to do that is because that insulation, if it compresses, creates a void between the insulation and whatever the floor covering is or surface covering is. Most of the time it's concrete. If that compressive area gets too big and that void gets too big, then over time, repeated vehicular loading on that point will cause the concrete to crack. You create risers in the stress risers, and it'll just crack. So you have to be accounted for that and make sure that you choose the right insulation. Well, 2-inch insulation costs way more than a 1-inch insulation board does. So there's a cost factor, a hard cost factor associated with the insulation itself. Let's look at an example. If I have my cost per therm is $1, and these numbers are illustrative. They work somewhat based on reality several years ago, but the logic holds true. Cost per therm is $1. If I estimated cost for the insulation at 75 cents per square foot, the cost to insulate 1,000 square foot driveway is $750. 1,000 square feet of area to melt. If I insulated it, assuming a 20% variance in loading, would be 125 BTUs a square foot, and without insulation, 150 BTUs a square foot. I'm accounting for that added loss into Mother Earth, basically. Higher BTUs to operate an uninsulated slab, no question. When you look at the cost of the BTUs, that difference of 25 BTUs per square foot is about 25,000 BTUs in additional loss. Average a 4-hour runtime is 100,000 BTUs. It's a therm of BTUs. It's $1 per event that you're looking at. But the cost in the insulation is way higher than that. So the return on that investment in this example is 75 years to pay for the insulation. So there's a lot of factors that go into whether I want to insulate or not. Some of it's performance, some of it's responsivity, some of it is BTU loading, a lot of things. No right answer. Just be aware of what the factors are so you can make a better choice. Installation, typically a couple things to keep in mind on hydronic systems specifically. We want to make sure that the tube spacing is fairly consistent. 6, 9, and 12 inches on center is typically what we see. No wider than 12 inches. Hot to cold. The coldest surface on a snowmelt system is the surface. Heat's going to want to migrate vertically naturally, and it's going to want to migrate vertically before it migrates horizontally. And there's a distance here that if you get farther than 12 inches, basically you end up with an unmelted section in between the runs of pipe. And instead of having a nice, clear, snow melted surface, you end up with what looks like a candy cane. You have stripes of snow that can't be removed. So no wider than 12 inches on center. Make sure the tubing is at least 2 inches, if not maybe 3 or 4 inches down from the surface of the slab. Part of that is for the vehicular factor, the loading, the dynamic loading on the slab. You need to make sure the tubing's deep enough to be inside of the load triangle that's formed inside the concrete. If it's too shallow, it falls outside of that, and it actually becomes part of the stress riser and can induce cracking. The other thing that happens is in concrete, we're dealing with a physical aggregate, the stone. That aggregate is about 3/4 to 1 inch in diameter, typically, depending upon the slump of the concrete. We want to make sure that the tubing is deep enough that that stone can float in the surface. We don't want to have a situation where it's surface stone tubing, because that will induce spalling on the concrete and it'll kick that stone out, and you have a hole now that actually could expose the tubing. And finally, the last thing we want to deal with is post-concrete pours can induce saw cuts as crack control. Saw cuts typically take place about 1 inch to 2 inches in depth. we want to make sure the tubing is deeper than what the projected saw cut depth is going to be. I don't want to run the risk of inadvertently cutting tubing because I'm cutting in a crack or a joint control on the slab. A lot of on the electric side, you're dealing with mats, you're going to deal with cables. Those are the two primary types of product that you'll see. Mats have an advantage because the cable is pre-spaced. You just roll out the mat. It usually ends up being a faster installation. Ideal for squares and rectangular spaces where you're running straight out, you turn, you run straight back pretty quick. If you have a unique shape area, driveways or parking lots that have curves or nooks and crannies that have different jut outs to them that you have to try and cover, a cable may be easier to install because you can conform it to whatever the shape is. Both hydronic and electric typically use mostly the same controls, same type of sensors that are monitoring the snowfall area. The only difference is that the controller is either energizing a relay or a contactor to send power to a resistive cable, or it's energizing a relay to send power to a circulator and a boiler. Applications that we typically see, concrete slabs are the primary ones that you'll see for snow melting, followed closely behind with brick and sand and brick paver applications. Tubing is going to be embedded in the concrete, as we mentioned. If it's a sand and brick paver, it's going to be embedded in the sand bed below the brick. And you want to make sure that when a sand and brick paver system is installed, they lay down the sand, they put the bricks on top, and they usually vibrate the bricks down into the sand bed. And that draws up the sand between the bricks and locks them in place. We want to make sure that we have enough sand and that the tubing is low enough, or the cable, that it has about a 1 inch of sand between the top of the pipe and the bottom of the brick after compaction. We don't want to have the brick sitting right on top of the tubing. One, that introduces wear over time on the cable or on the pipe. And also it causes that tubing or the cable to be part of the structural element. It actually starts to see some of that vehicular weighting potential. And again, it adds to wear over time. Most of the time, a brick is going to be 2 5/8 inch thick. Standard pavers are fine. In a lot of areas, maybe resorts or different areas of the US, you might see bluestone. You may see thicker stone that can get up to 6 inches. Keep in mind that the thicker the floor covering, the farther the tubing or the cable is from the finished surface of the floor, is going to require a higher water temperature to drive the heat up and to get the surface to the necessary temperature. Anything that is approaching 6 inches, 4 to 6 inches in stone covering, is a gray area on whether or not we can do that. Mathematically, you're going to be running way higher temperatures, and you just need to make sure that everything's accounted for properly. Asphalt can be used. A lot of times asphalt is recommended or used as a floor covering or a driveway surface covering because of cost. It costs less than sand and brick pavers, and it costs less than concrete. You can use it. Keep in mind the following, though. Asphalt has half the conductivity of concrete. Concrete has a conductivity of 0.81. Asphalt has a conductivity of 0.42. What does that mean? Well, that means that I'm naturally going to have to drive my snowmelt temperature up to a higher fluid temperature in order to get through the added resistance of the floor covering, so that my snowmelt surface is at the temperature it needs to be. Asphalt is typically laid hot with heavy equipment. So I usually will see the tubing in the gravel bed below the asphalt to protect it from the heavy equipment. You can't drive on it. So you're 2 inches down into the gravel. You have 3 inches of low resistive material on top. All those things come into play and say, I need a very high fluid temp. It's not unusual to see a fluid temp of about 160 plus degrees for asphalt. And that's fine. It's not an issue. My boiler's running at 180. I have the capacity. Here's where asphalt systems tend to lose their edge. Asphalt is a fluid. It is always moving. It's dynamic. And over time, you're going to end up with dips and craters and potholes and other things, as especially where vehicular traffic is. You get ruts. We see it all the time in every asphalt area we experience, from the gas station to the grocery store. Same thing happens here. In order to fix that, they resurface the asphalt and they add a layer on top. They do that. Every time they do that, adds resistance over the tubing, and it causes me to have to up the fluid temperature. The more I do that, the higher the fluid temperature gets, and my limit now is the boiler temperature. Once I hit the boiler temperature, I cannot get any hotter in the slab area, and so there is a finite life to an asphalt system from the hydronic perspective. Operating costs, those are going to vary depending upon your design factors. Excuse me. Sorry, had to sneeze. My apologies. Your percentage of confidence is going to drop. I'm sorry.
So just before we get into the costs, we had a couple of questions come in the last little bit on kind of some of the installation points that you covered there. Obviously, we were talking a lot about, above and beyond, or above and below the piping, but we didn't talk a lot about the actual piping arrangement itself. Could you comment just briefly on, I guess, like serpentine layouts versus the counter current layout? I know the diagrams, the depictions were generally showing kind of that counter current layout, correct? Is that the best practice?
Well, okay. So best practice is kind of, that's a gray term in this case. There are different patterns that you will use, sometimes based on the product used. And really it's going to be based on how easy it is to install the product. So let's start with electric systems. Electric systems, it doesn't matter. The cable is the same temperature regardless of where it is in the mass. At point A is the same temperature as point B. So that I can lay in any direction, any shape, any whatever. I can write my name with the cable. Doesn't matter. The only thing that I have to maintain is the wire spacing. So cable is pretty simple in that regard. Hydronically, you have two types of layouts. You have a serpentine pattern, which is basically the tubing goes out and back, out and back. It's a linear pattern, and then it returns. And then you have a double serpentine pattern, which basically doubles the pipe up on itself. And it runs the return line right next to the supply line. So you're running this loop that has the supply and return next to itself all over. And that loop is a serpentine pattern, but it's a compound pattern, if that makes sense. Wish I had a whiteboard. And the difference is the serpentine pattern loses temperature linearly along the length, right? And so across the surface, let's say that the starting temp is 140 and the ending temp is 110. So I get a gradient across the surface of my snowmelt until the entire mass comes up to temperature. The double serpentine is almost even though I have a 140 and a 110 on supply and return, the temperature in between is even all the way along that loop. And you get a much more even melting earlier. They both will melt eventually and clear the space. It just depends upon what your performance factor is from a design standpoint. The single serpentine is easier to install. It'll be faster to install. It'll take less labor to do it. The double serpentine will take a little bit more time, and it'll be a little bit higher labor cost to do that. And so now you have to kind of weigh your pros and cons between install cost and performance variance, if that makes
That
sense.
goes back to that, the like the ambulance having the factor of 1 where you can have no accumulation, correct?
Correct. Yeah, if that is a critical factor, that surface is entirely smooth and ice free all the time, a double serpentine may be what you want to consider from an installation standpoint. Absolutely.
And then I guess one thing I'll note, we are at the end of our
Yeah.
allotted time. We'll continue on here for those that have time to join us. If you do have to jump off, we really appreciate you spending the time with us that you have. If you have any further questions, if you need help on a project, please feel free to reach out to me. I'll loop in Colin. We can have a joint conversation on that. And then as well, we had a couple more questions coming in, so we'll
Yep.
just continue right along. On the life expectancy, and you're probably covering this in the operating costs and probably the next versus lifetime costs. What is there a different life expectancy for electric MAC systems versus hydronic systems?
Yes and no. So we've been doing electric snow melt for 25 years, give or take. And I have yet to see a snow melt electric system fail because the cable failed. I have seen systems fail on hydronic and electric over time, and that's almost always due to in some external environmental source. The slab cracked and shifted. Somebody came through and did a saw cut. They did something to the area and they damaged the cable and damaged the pipe. But normal operation on electric systems, I honestly have not seen the cable have any issues. Controllers are a different story. The control device, the contactor relays that switch power to the electric snow melt system, those things will fail. They have a set cycle time. They'll run X number of active on-off loops, and then they're going to give up the ghost, so to speak. But that's true with any relay. Anything mechanical like that has a finite life. Those are the things also that'll be susceptible to power surges. Again, it's an external factor, but things that can happen. On a hydronic system, that again, the tubing is not going to be an issue. What's in the slab is not going to fail on you. What you'll have to worry about on a hydronic system is maintaining the glycol. You're going to have to replace pumps every so often because they'll fail. They'll just run out of their life cycle. Boilers will have to be replaced eventually. Now, whether that's replacement every 5 to 7 years or every 20 to 30 years, depends upon how often the system runs, depends upon the duty cycle of the system, a lot of factors, right, that go into that. So some of the components will fail just because that's just the nature of the beast. But the tubing and the cable that's in the snow melt, there's nothing that comes to mind that causes me to say, oh yeah, this is an organic failure point. It's almost always externally driven.
Yeah, that makes a lot of sense.
Okay. Any other questions at this point?
No, we're good. We can keep running.
Keep going. Okay. So operational costs. This is just an example of 98% what the BTU load would be, and if we ran it so many times, what the difference could be between a natural gas and an electric system, and it could be significant. That annual cost, even though it's more for electric, may still be less from the cost it takes to install the system over whatever we deem the lifetime of operation, right? So it's not always as cut and dried as just saying, oh, it's a flat cost of X. There's other things that we need to look at. Idling systems, this is relatively old school versus new school. Idling systems used to be, we needed to run the system 24/7 to make sure this area stayed free of snow and ice. We don't really idle anymore. We talk about idling because the mechanics are still there. The intended goal of operation is still there, but we've augmented it with the controllers. The controllers now are smart controllers. They preemptively start the system before snowfall starts. So it comes up to temperature before snowfall happens, and you get the same effect as idling. Whereas in the past, we didn't know that we didn't have smart controllers, didn't have internet, and you didn't know when it was going to snow. So your only option was to run it 24/7. And that just was really wasted energy. It just didn't do you any good. Projects did it, projects that had an unlimited supply of heat did do that. And you're like, well, who has an unlimited supply of heat? Well, steam systems, they captured waste steam, they captured waste heat off of an operation scenario. There's a lot of heat that's available that is vented to the atmosphere that can be reclaimed and dumped into a snowmelt system. We do a lot of grocery stores, ironically. They tie into the freezers and they reclaim that heat for the portico. We do ice rinks. They're extracting heat out of the ice, and that extracted heat is being vented. Well, if you throw on a reclaim unit and you capture it, you can run a snowmelt system, right? So there's a lot of systems that will idle and will run 24/7 on free energy. So it's still done, but really preemptive systems are the ones that we see more of. Okay, so question: what is the most common snowmelt size? What is it that you're typically seeing requested from a design?
I'll jump in, just kind of keep it moving along.
Yep.
I would say the most common we see is probably that parking garage ramp or like an ambulatory space.
So a couple hundred square feet or less, maybe.
Yeah, sounds about right.
But you may have a lot of them, right? So you may have 300, 300, 300, right? Depending on how many entrances or ramps you have. So yeah, there's
Like
really
the
no
walkways around the hospital probably as well, or like the promenade of an area.
Yep, those are all good areas. Yeah, snowmelt systems tend to be smaller than they are bigger. Ironically, people think of snowmelt being huge, and they're not. They're usually very point of use, very specific areas. Okay. These are the controls real quick. Smart controls. There's going to be a sensor that is in the slab area. You actually can have a puck that sits in the slab. It's going to monitor snowfall. It's going to monitor slab temperature. It's going to monitor all the environmental conditions. You can also have a pole mounted sensor that is more retrofit. And you're like, well, why would you ever need a retrofit? Well, ironically, sometimes the slab gets poured and they forgot to put in the sensor. It happens. Miscommunication. The snow melting guy, the electrical guy didn't talk to the concrete guy, and suddenly the concrete's poured and there's no sensor. So you can retrofit and use a pole mount as well. The controllers can be chosen to run the pumps, to run the boilers, to run all the components in the system as well, just depending upon what it is that we need it to do. They can be easily be sized and set up to have different lead lag times. There's warm weather shutdown and cold weather shutdown, so that the system doesn't run in these fringe temperature regions that we either know it's not going to snow, or it's not, or if it does snow, it's going to be melted on its own, right? So this is just some more examples of what the pole mounted versus the slab sensor looks like. Setting up a system hydronically, we can look at isolating the heat source with heat exchangers. We can look at doing mechanical mixing, motorized mixing. We can do injection pump mixing. There's a lot of factors that we can go into to control the water temp out to the slab. Variable speed mixing systems allow me to have variable temperatures, so that when it gets colder, it automatically ramps up the temperature to the system. So I get my more constant, more steady response out of the system. There's definitely a outdoor temperature versus load factor, all on a sensible load that brings the mass up. The controllers will compensate for that. The controllers will say, oh, it's 30 degrees versus 0 degrees, and it will automatically adjust the performance and operation of the system to help compensate for the response and lag of having to overcome the mass temperature. There is one thing to talk about, especially the difference between hydronic versus electric systems. When you talk about max supply temp in any hydronic system, almost everybody's going to say 150 is the max you can run temperature in a slab. And that's true to a point. The question is where did the 150 come from? The 150 came from old electric snowmelt systems that were installed in the 40s and 50s. Those systems went in without any control or regulation. It was literally a cable in the slab hooked to power, and that was it. When you flipped the switch on that thing, that wire got hot instantly everywhere, and it was an unregulated wire. And so the wire temp could have easily been 250 degrees. And it was almost always placed fairly shallow in the concrete. They would pour out the concrete and put in the wire and then skim coat the top, or the wire floated up. It was almost always near the surface of the concrete. So you had very little mass above the wire, very little diffusion area to diffuse the heat that was being produced. And when the wire or the switch was flipped, that wire was instantly hot everywhere. And there was no way the concrete could absorb that much energy and adjust itself. So therefore it cracked. It was deemed that shock happened above 150 degrees electrically. That rule has become the standard in the industry today. Hydronically, I argue that it's nearly impossible to shock a concrete slab hydronically. And the reason why is as you move water through the tubing, that water is losing heat to the mass as it moves through. So the supply temp on the supply side of the tubing will be 140. And on the return side, on startup, is going to be 0. It will give off all its heat to the mass along the entire length of the circuit. And so the concrete slab has this gradient in it, and it is no longer shocked as having all that temperature confined across the entire mass. And as the temperature of the slab comes up, the return temperature starts to come up. And so you start to approach our desired design delta T in the system over the initial couple of hours of response. Very, very difficult, if not impossible, to hydronically shock a concrete slab, but very, very possible to do it with an electric system. Either way, if we keep the water temp and or wire temp below 150, we're guaranteed not to have an issue. Hydraulically, though, I have seen systems run hotter than 150 with no issues. But just understand where that rule came from and what's happening dynamically in the system, and know that you have some flexibility. Sand and brick paver systems, I'm not worried about it because I'm in sand. It's 1,000,000,001 cracks already. I'm not going to worry about it. Again, can't shock it. And asphalt, same thing. It's a fluid. It's always moving. You're not going to shock asphalt. Really, the only time that you have to worry about shocking anything is concrete. Redundancy controllers are fail points. They can fail over time. So a lot of times people will install multiple sensors. So all they have to do is switch between sensor A and sensor B. It's a backup. Do you need to? No, but it does give some end users and project owners a warm fuzzy and a sense of confidence that they can switch between the two. If it's a really large area, you may install multiple sensors, and get an averaging across the large area and not be reliant on one spot. This comes into play depending upon the shape of the area. You can have building shadows that cast or buildings that cast a shadow across an area. That shadow can impact solar gain. It can impact temperatures of sidewalks versus parking lots. It can impact drifting of snow. It can impact a lot of factors. So sensor placement is critical on knowing the performance and responsivity of the system as a whole. Having multiple sensors can allow me to maybe make adjustments based on how the environment impacts the performance. Controllers can also be chosen to allow me to have multiple zones. The controller can be smart enough to say, okay, I have 4 zones in this case, and I am going to run these zones in sequence. Zone 1 runs until it melts. Zone 2 runs until it melts. Zone 3 runs until it melts. The advantage to this is if I were to look at all 4 zones together and size as a contiguous system, I may need a million BTUs to melt all 4 areas. However, if I set them up in a rolling configuration, now all I need is 250,000 BTUs to melt each section or quadrant, and I can get away with a much smaller mechanical system and still get the same melting across all the areas. The trade-off is time. It's going to take me longer to roll between the 4 than if I just melted them all at once. But it is a design variable that I can play with. Smart and connected. Most of the smart connected controllers allow me to log in on my phone. I can be remote. I can see what the system's doing. If it's a secondary home, for example, and I'm going up on the weekend, I can remotely turn on the system to melt ahead of time. I can remotely turn off a system to get it to stop if I'm not going to be there. A lot of good connectivity control points with the smart controls. Hydronic panels, a lot of solutions out there to set up the mechanical room. Installers can pipe on site the mechanical room. You can order pre-configured panels to help speed up installation times. As long as the piping fits the application, that's the key, right? And these are also customized panels depending upon what the system is calling for. A lot of different configurations out there that can be pre-piped to help save time on the job site. Hydronically talking, there's a lot of different tubing options out there. There are EPDM products, there are PEX products, there's PEX aluminum PEX or other composites, there's PERT. They all do the same thing. They all deliver BTUs and temperature out to the snowmelt area. Which one is better is going to be dependent upon personal preference. Which one am I comfortable using? It can also be dependent upon application. There are pros and cons to each of these. PEX is kind of the industry standard these days, but PEX has limitations relative to UV. The colder it gets, the harder it is to work with. Snowmelt systems ideally get installed in the summertime, but not always. So sometimes you're fighting the elements to install the pipe. EPDM tends to be more flexible, tends to be more weather resistant, but also tends to be more expensive. So there's some pros and cons there across the board, depending upon what we're looking for on the job. Pattern of layout we had mentioned earlier, double serpentine versus single serpentine. The EPDM products tend to be easier to install in the double serpentine, whereas the PEX tends to be more rigid. So if you're looking to do a double serpentine pattern, an EPDM may be a more advantageous product. Distribution piping on a snowmelt system, you got to get the heat out from the boiler out to the snowmelt. That typically means going outside and running outside for some distance. Pre-insulated piping just helps minimize the BTU loss between point A and point B. So we're optimizing everything that we're delivering out into the snowmelt area itself.
So this is where one of the questions earlier on came in, and we're just waiting to bring it up. Is there any considerations for above ground manifold like cabinets?
Um, Not from my perspective. Really, my requirement on a manifold enclosure is that it is free from the elements. It's not sitting in water, so it has drainage, and it is sized to handle whatever loading is on top. So if it's in a walkway, then it just needs to handle pedestrian traffic. If it's in the actual driveway or snowmelt area that can experience vehicular loading, it needs to be more robust to handle that load. Some installers will use landscape factors and um, elements to like fake rocks and those type of things to hide the manifold enclosure from view. Those are all fine. We don't really have any say over how that's done other than keep the manifolds accessible, keep them free of water and debris, because you need to get in there and you're going to need to maybe adjust and balance the manifolds. You're going to need to vent purge the manifolds, especially if you have to purge the system and refill it with glycol down the road. You're going to have to purge the manifold. So keep them accessible, keep them free of debris, and keep them in an enclosure that can handle the loading of the environment.
So on the location side, obviously the picture you're showing there, it's very close to the loop.
Mm-hmm.
There's an application where someone's asking, it's for ramps for accessible areas. The manifolds are most likely located in the basement, lower than the loop. Are air pockets in the piping up at the high level loop going to be a concern? And I guess that ties into the venting that you were talking about, right?
Yeah, so the answer is yes. Be aware of it. Is a concern? No, but it is a factor. And there's actually two factors in that scenario. So I'll address the purging first. Normally, the manifold would be the highest point. That's ideal. Manifolds have the vent purge on them. You just purge from the manifold highest point, ideal. In that case, where the tubing is the high point, you don't have that luxury. So what we typically recommend is what I have referred to over the years as a power purge. On your manifold, you have mini ball valves. You shut off all the circuits but one. So if I have an M5 manifold with 5 circuits, I close 4 of them. That forces all the water through one circuit. That increases the velocity through that one circuit, and higher velocity will reabsorb trapped air and train it back into the water to get it back to the main system micro bubble air remover and vent it that way, or allows you to purge it back at the main boiler purge potentially. And when you get all the air out of circuit one, you close it and open up circuit two and just move right down the manifold circuit by circuit. The other thing that you have to take into account is if my manifold is in the basement and the snow melt is 15 feet above me, right, in a parking garage or whatever the case may be, that 15 feet is an extra 30 feet per circuit that's not contributed to the snow melt area. In the design, I have to account for that distance. So if I were to put the manifold in as shown on this picture, right at the point of use, basically my distance to and from the manifold in the snow melt is zero. Almost 100% of the tubing designed is used in the snow melt. In my basement scenario, so in this case, let's say my circuits came out to be 200 feet in length. In the basement scenario, one of two things are going to happen. Either A, I keep the same number of circuits, but now I'm designing around 230 to 250 foot circuit runs. Longer runs mean higher pressure drop means bigger pump. Or in order to get the same coverage area at 200-foot circuits, I need more circuits. So I go from 5 to 10 or 5 to 8. I'm adding more loops. The other factor to be aware of is the surface area itself requires a minimum circuit length. So if I have a square that's 50 by 50 and my manifold's in the corner, to get to the far point, I got to go 50 and 50. That's 100, 50 and 50. That's 100 back. A minimum circuit length is 200 feet. If I drop that manifold away from the zone and I keep my 200 foot circuit lengths, really I'm only have 170 foot runs available. I'm going to be short. I won't be able to hit all the area that I need to cover. So we need to account for that manifold position relative to the snowmelt area during the design process, so we can account for the proper length and the proper number of circuits to account for that added distance. It's kind of a long answer to a simple question, but that's how we look at it.
Thank you very much.
Yeah. Oh, there are also a lot of manifold options on snowmelt systems. There's copper tube manifolds, there's stainless steel manifolds. There's a lot of great ones. There's polycarbonate manifolds. Almost all of them have flow meters on them nowadays. Do you need flow meters? No. Are they nice to have? Yes. It allows you to balance out the manifold a lot easier. It's not a requirement, but it is a nice to have. So just keep that in mind when you're picking your accessory items. Okay. Oh, this is kind of what I was talking about. Flow meters are great to have. Temperature gauges are great to have. You can balance a system, especially if you have multiple circuits or multiple zones. You can balance out by delta T's. A lot of accessories are nice to haves, but not necessarily requirements. Just know what your system design is and what your needs are will dictate what accessories you should select. So what types of tools do you normally use when quoting and designing a snowmelt system? And I apologize, I am really running late.
Yeah, we had a lot of great questions that really got us sidetracked in wonderful ways.
Yeah,
I hope that most people are saying they use a lot of ATS spec tool.
Yep.
That's my goal. I will take over just for a second here.
Yep.
And well, not fully take over, but yeah, just mention that we do have the new electric snow melt systems on the spec tool. If you're familiar with ATS spec tool, when you're on the categories page, you can just search snow and you'll see the controllers and all the different products that are associated with it. If you've not seen the spec tool, reach out to me directly, zach@atspec.com. And I'll get a demo set up for you so you can get a one-on-one intro to spec tool. But I know we're running quite long today, so I won't take the time with the demo. Yeah, we haven't really seen any additional coming in. I know you guys do have a specific snow melt system designer, correct?
Yeah, there are a lot of tools out there in the market that you can use. And there's really no one that's better than the other. Just understand what the tool requirements are and what the outputs are. Almost every computer generated design tool is what I call it's not smart. It's whatever information you put into it is going to drive the output. So as a designer, you just need to understand what the outputs mean and what variables drive those outputs. And if a snowmelt system design says, "Oh, I can't heat it," understand why. And it could be that, oh, well, my conductivity was off, or oh, my thickness above the tubing was misentered. There's a factor in there that's driving that output. Understand what that output means and what factors go into it, and it's going to allow you to troubleshoot your design better. Knowing the rules of thumb, knowing the swags for design factors are good elements to help you catch what looks right versus what doesn't look right. So there's some old timers out there that have some good rule of thumbs that can help you in that process. And then finally, there are like another option. There's a lot of support tools out there from each manufacturer that I'm sure they have their own flavor on tools to help select. Watts's selects it. It's on the website. A lot of different tools to help that. Let's see. And that's it. That is the end of the presentation, finally, right?
Well, I know last week we ran a little quick. We covered the content in a short amount of time. So you're just bringing the average right back up to the hour. That's all that happened here. We appreciate it. That was great detail, great questions from the
Right.
audience. Really appreciate you spending the time with us today. Obviously, these snow melt systems can get quite personal to your project. There is, yeah, there's rule of thumbs. Yeah, there's standard practices. But if you want help getting your specific project design, feel free to reach out to me. I'll loop in a conversation with Colin. I know one of the people in the audience reached out earlier, said that they've got a specific project they're going to ask for a hand on. So feel free to reach out to us. We're happy to help you get the right product and the right application. And if you need help either getting into your selected system or finding those products and configuring those products on the ATS spec tool or the Watts spec hub, feel free to reach out to us for that as well. And thank you so much, Colin. That was a great presentation. I learned a lot, and I've been working with Snowmelt for a number of years already as well. So there's always something new you can learn.
Always something.
And I see the final question coming in. Do you get a certificate? Of course, yes, you absolutely do. This is an ASPE CEU certification. You'll be able to self-report as well. All ATS universities, we send out a certificate of attendance so that you can have it for your records for any of the different reporting systems. I know some require accreditation, some just require a learning forum for self-reporting. So we handle that with our certificate of attendance to all of those. So we'll be having that out. And if you need more of those for more hours, we'll have more system design presentations shortly. I think next week we've got a product presentation on, I think it's water and energy conservation for a faucet company coming on next Friday. So jumping from topic to topic. We'll have more ATS universities soon. Once again, thank you all for spending your time with us today. Thank you, Colin, for a wonderful presentation. And if you have any questions, please feel free to reach out. Enjoy the rest of the day, y'all. Bye for now.
Sounds great. Appreciate it. Thank you.